Hello, I'm Jonah.
And I'm Yesh.
And we are the two co-first authors for this talk. There's a really astounding breadth of dynamic behaviors that we see in nature. Animals can hop, gallop, walk, run, skip, and most impressively, they can smoothly transition between these behaviors. The fact that this is possible with a single biological whole-body controller seems to imply that there is some sort of continuum or a spectrum of bipedal gaits. We want robotic control policies to be able to mimic this impressive array of gaits and behaviors. We think that reinforcement learning is uniquely positioned to endow robots with this ability because it allows for complex and largely unspecified behaviors to emerge from simple and easy to compose reward functions. The question is, which reward functions do we need to use to get there? In this work, we show a method for describing reward functions in the setting of sim-to-real reinforcement learning for achieving robot behaviors that span the continuum of all common bipedal gaits. A commonly used approach for applying reinforcement learning to robotics is to use reference trajectories to guide learning. Typically, a trajectory of joint positions is used to create a bedrock reward function, and the policy has to maximize that reward function by imitating the original reference motion as closely as possible. However, it can be difficult to obtain reference trajectories for a particular motion, and even more difficult to ensure that these trajectories are optimal or even feasible for robot hardware.
Reference trajectories can also limit the way your policies explore the environment during training. If reacting to a disturbance or responding to the environment in some way results in a trajectory of joint positions too far from the reference, the reward will be needlessly low. This limits the type of experience the policy can collect and can stop your policy from learning robust or error-correcting behaviors which happen to stray too far from the reference motion. There's also the question of switching gaits. Once you've learned a walking controller from a walking reference trajectory, can you somehow extend that to hopping? And say you have two reference trajectories, one hopping and one walking, how can you switch between them smoothly? These are questions for which there is no good answer for if you are in the framework of reference trajectories. On the other hand, clearly, some sort of reward structure is obviously necessary. The type of reward function used in the policies shown in this video won't work on hardware because it is too underspecified. In addition, by using such a simple reward specification, there is no way to command a particular type of desired gait, such as running instead of walking. So, how do we write a reward function for bipedal locomotion which is neither overconstrained nor underspecified?
Let's take a look at the simplest legged gait, a monopod hopper. By simple inspection, we can immediately notice two things. One, that the forces applied to the foot end effector of this hopper are going to be zero during the swing phase when it is flying through the air, and large during the stance phase when it is in contact with the ground. Second, we observe that the translational velocity of the foot end effector is going to be zero during stance, provided that the foot doesn't slip, and large during swing when it is moving through the air. Using these observations, we can craft a very simple reward function to learn a policy which encapsulates this behavior. We want no forces applied to the foot end effector during swing, and we want the foot end effector to have no velocity during stance. So, we introduce a phase time variable phi, which tracks our gait cycle and splits it up into two chunks of time, swing and stance. From here, we do a simple if-else check, penalizing large foot forces if we are in swing and should be in the air, and penalizing large foot velocities if we are in stance and the foot should be firmly planted on the ground. This way, if we have large forces during swing, our reward will be very low. Likewise, if we have large velocities during stance, the reward will again be very low. But we're not quite done yet. There are some problems with using a step function. For one, we don't actually know when the precise best time to lift or place the foot is. Contact can happen slightly early or late, and we want to build in some wiggle room around when touchdown and liftoff should occur to let the policy figure out a behavior that is appropriate for both robot morphology and the terrain. Another way to phrase this is that we want to build in some uncertainty around the transitions between phases. We use a probabilistic model of the transition timing by making the transition point between phases a random variable. Now, our transitions are subject to some randomization, and we've captured the uncertainty about transition timing that our step function couldn't. This yields an explicit distribution around the time of transition between each phase, and we can modify its positional mean and variance. Since we parameterize the phase transition point with a probability distribution, we can calculate a probability that the swing or stance phases are active given the phase time phi. Using this probability, we derive an expected value of the coefficients c sub force and c sub velocity based on the current phase time phi, and use that to determine how much to penalize foot forces and foot velocities. By adjusting the variance of the random variable, we can make the expectation steeper or smoother around the point of transition.
Now let's try to extend this to bipedal hopping. But first of all, what is hopping? For both feet, entering a swing phase and then switching to a stance phase at the same time leads to this behavior. We can use unipedal hopping to describe the left foot stance and swing transitions, and use a parameter r for the ratio of time spent in stance. By changing r, the left foot will spend less or more time on the ground versus in the air. The cycle diagram for the foot force cost is shown here. The velocity cost would simply be the opposite sign. To add the right foot, we simply duplicate the behavior description of the left foot. The ratio parameter r is common for both feet, which enter and exit their swing and stance phases at the same time. Both feet together create hybrid phases that define their composite behavior. When the left and right feet are in stance, the robot is grounded. When both feet are in swing, the robot is in an aerial phase. By adjusting the ratio parameter r, the time spent in the air can be increased or decreased. Now that we have hopping, how would we describe a behavior like walking? Unlike before, both feet are now synchronized in opposite phases. Another way to view this is that over the entire cycle time, one foot swing and stance phases are offset by half of the cycle. We can introduce this offset with new parameters for the shifts in the period of the cyclic clocks of each foot, theta left and theta right. When the offset between each period shift is 0, like before, both feet follow synchronized clocks and we get hopping. When this difference is 0.5, or half of the cycle time, the feet will be diametrically opposite in phase. In this setting, when the ratio parameter is set such that the time in stance is greater than the time spent in swing, the behavior is alternatingly picking up one foot while keeping the other foot on the ground. This is walking. Instead, if we set the ratio parameter such that more time is spent with the leg swinging, we observe a running behavior. The grounded phases have been replaced with an aerial phase. We can actually use the parameterization of a common swing-stance ratio and individual shifts for each foot to get the full spectrum of all 2-beat gaits. When the shift between both feet is somewhere between 0 and 0.5, the resulting behavior is galloping. Like with walking and running, adjusting the ratio parameter to put more time in swing results in behaviors with more time in aerial phases. By making these parameters knobs that an end user can control, we are able to continuously switch between any of these 2-beat gaits.
We can transition from any gait to a standing behavior by increasing r until it encompasses the entire gait cycle. This is a gait where the entire cycle is just one stance phase. This is an interesting extension of the gait parameterization, given that people usually don't consider standing to be a bipedal gait. We can also transition from walking to hopping by sliding the period shifts for both feet to be the same. This sliding process can be discontinuous, and learned policies will transition to the new gait within 1 or 2 steps, but it can also be done smoothly across time, as the policies were trained on the full spectrum of possible 2-beat gaits. Here, we transition from walking to running by decreasing the ratio parameter while the policy is running. As this happens, the robot smoothly transitions into a more bouncy gait with an aerial phase. I think it's important to remember here that there is no trajectory generation step, and these behaviors and transitions are entirely learned by the policy without any reference beyond the foot force and foot velocity penalties.
So it's great that we can transition between all of the 2-beat bipedal gaits, but what about something more complicated like skipping? Unlike the other behaviors, skipping cannot be described by just one swing and one stance phase per foot cycle. We were able to define skipping by using 4 phases, 2 swing and 2 stance. This was done by defining the 4 phases such that the ratio sum to the cycle length, which is 1. This extension of the framework is capable of expressing more complicated gaits such as skipping, but also more sparsely populated with feasible gaits. While the reasonable training procedure for the 2-phase model would be uniformly sampling commanded ratios and period shifts, doing so in the 4-phase space results in sampling many more infeasible behaviors for the robot. In practice, we defined reasonable ranges for sampling commanded behaviors, and the learned controllers were capable of transitioning between any behaviors in that sample space. In the larger 4-phase space, we were able to continuously transition between running and skipping by defining both as four-phase behaviors and sampling commands from each during training.
Now that you've seen a few of our hardware results and the intuition behind defining legged gaits using our framework, you may be curious about some of the more technical details. The actual inputs to the learned controller are the ratios and shifts which define the behavior specification as well as the velocity command and the robot's observed state. An important part of our approach is that we use a traditional, proven training setup with nothing novel or fancy. We use proximal policy optimization with an LSTM controller, train and simulation using dynamics randomization. The controller outputs PD set points and gains at 40 Hz for an underlying PD controller which runs at 2 kHz. Using this setup, we found that we can reliably transfer learned policies directly from simulation to hardware. Additionally, we use a mirror loss term to encourage symmetric locomotion and have auxiliary reward terms for commanded orientation, velocity, and motion smoothness. Some preliminary results suggest that the action and smoothing terms may not be as essential to the sim-to-real process as we had originally thought, though we have not yet done a formal ablation study on their importance.
Now we have a principled way of defining the cost of legged locomotion within the framework of sim-to-real reinforcement learning, and we have shown a generic controller for all common bipedal gaits and can learn more complex gaits like skipping. How do we further improve robot capabilities with this method as the foundation?
It turns out that by simply adding ascending and descending stairs to the simulation randomization procedure, this same method can result in policies which ascend and descend stairs despite being completely blind to the world. This suggests that the policy's behavior specification and its training for robustness in simulation are two separate problems which can be improved upon independently in the framework of sim-to-real RL.
Additionally, while the results are for the blind bipedal robot chassis, the same approach has no specific provisions for particular robot hardware and works in simulation for other bipedal models such as Agility Robotics Digit and the Humanoid V3 model from OpenAI Gym. The framework is extensible to any legged robot morphology, including quadrupeds and other non-bipeds. We'd like to thank our fellow lab members for their collaboration, the funding agencies of our lab, and Intel for access to computational resources. Thank you for watching our presentation, and please feel free to ask any questions you may have.